All right, in this lesson, we're going to talk about how we use Lewis dot structures to show the bonding in covalent molecules. So the first thing that we need to discuss is what exactly different notations mean in Lewis dot structures. So when we draw these, you probably remember from 3.1, dots represent electrons. So we can represent electrons using dots, or when we want to show a bond is formed between atoms when they share 2 electrons. So we can represent a bond using a line or using 2 dots. So for example, a bond between carbon and oxygen could be shown like this or like this. Those are equivalent. Every atom is trying to share electrons to have access to 8 like the noble gases. We call this the octet rule. Now there are a few exceptions. The most notable exception is hydrogen, which only needs 2 electrons. Now the reason hydrogen needs 2 electrons is that hydrogen's noble gas is helium. So when hydrogen is gaining, or sharing electrons to achieve stability, hydrogen is really just trying to be the same as helium. All other atoms, except boron, are going to have 8. Boron is satisfied with 6. Now, when we talk about drawing these structures, there's a lot of steps that we go through, but rather than talking through these steps, I'm going to work through these steps with an example. So I'm going to use water as an example and kind of go through these steps bit by bit. All right, so when we draw water, our first step, or for any molecule, is to count the total number of valence electrons. So using our periodic table, we know that hydrogen has 1 valence electron, and there's 2 of them, and oxygen has 6. So that means that I have 8 total valence electrons. Now that means in my final structure, I have to use 8, no more, no less. Next, I want to arrange my atoms spatially so that I select which atom is in the center. Now, there's a couple rules that govern this. Hydrogen can never be in the center because it can only make 1 bond. Carbon is always in the center. And beyond that, the least electronegative atom is in the center. So here, hydrogen can't be a central atom, so I know it must be oxygen. So I'm going to arrange it so that oxygen's in the middle and hydrogens are on either side. Now, I'm going to start by connecting the atoms with single bonds. I know that they have to have at least single bonds because I know they're bonded together. So there's 2 electrons in each bond. So I've used a total of 4 electrons so far, which means I have 4 electrons remaining. Now, next I would distribute electrons to the outer atoms first and then to the central atom. However, in this particular case, the outer atoms are hydrogen, and they only need access to 2 electrons, so they're already satisfied, because the hydrogens can access both electrons in the bond. So I'm going to use my remaining 4 electrons on oxygen. We call these lone pairs. And lone pairs are electrons that are non-bonding, so they're only on oxygen, they're not being shared with hydrogen. All right, so to go back through these examples, first we're going to count the total number of valence electrons, which we did, arrange the atoms spatially, connect the atoms with single bonds, distribute the remaining electrons around the outside. We're checking to make sure every atom has 8 electrons. And if we don't have enough electrons to satisfy every atom, that's when we'll make double and triple bonds. So instead of just sharing 2 electrons, we'll share 4 or 6. And finally, when we're finished, we're going to count and make sure I have the correct number of electrons. Now, I'm going to do a couple more examples in a moment, but I want to talk about electron domains because those are going to be really important going forward. Every bonded atom, whether it's a single, double, or triple bond, and lone pair around a central atom is known as an electron domain. And these are going to help us determine the shapes of molecules later. So if a molecule has 2 lone pairs of electrons and 2 bonds on the central atom, how many electron domains would it have? it would have 4. 1 for each bonded atom and 1 for each lone pair. All right, so we already did water. I'm going to jump ahead and do carbon dioxide because that's an example. It's a little bit more complicated than what we did before. All right, so carbon dioxide, CO2. When I count the number of valence electrons, carbon has 4, and each oxygen has 6. So that means I have 16 total electrons in this molecule. Now, my central atom is going to be carbon for 2 reasons. One, we talked about how carbon is always a central atom, but also it's less electronegative than oxygen. All right, now I'm going to start with single bonds. All right, lovely. So I've used 4 electrons. I have 12 left. So now I'm going to distribute those electrons around the outer atoms. So I have 2, 4, 6, 8, 10. That oxygen satisfied. 12, 14, 16. That oxygen is satisfied. Now at this point, I have used all 16 electrons. This oxygen satisfied and this oxygen satisfied, but carbon is not, because carbon only has access to 4 electrons. So I'm clearly going to have to make some changes before I finalize my structure. Now, I could just take these electrons and put them on carbon. But the problem is that creates a new problem. Now these oxygen atoms aren't satisfied. I can't add any additional electrons, so what I'm going to have to do in this case is share more electrons. So I'm going to make double bonds between carbon and oxygen. So let's count and make sure we have 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. So that's good. This oxygen has access to 2, 4, 6, 8 electrons. Carbon has access to 2, 4, 6, 8 electrons. And this oxygen has access to 2, 4, 6, 8 electrons. So that structure is all set. Now, one other thing that you will sometimes see are polyatomic ions. So in the last topic, we learned about polyatomic ions, and we learned that these are covalently bonded ions with an overall charge. So let's look at drawing carbonate. Now, we're going to do the exact same steps that we've done before. Carbon has 4 valence electrons, and each oxygen has 6. Now, when we have an overall charge like this, if it's a negative charge, we're going to add that many electrons to the total count. If it were a positive charge, we would take away electrons. So that gives us a total of 24 electrons. Again, my central atom will be carbon, and I'll put the oxygens on 3 sides. I'm going to start with single bonds. I've used 6 electrons, and now I'm going to start distributing electrons around the oxygen. So I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, so I've used all 24 electrons, and all the oxygens are satisfied, but carbon still is not. So carbon only needs 2 more electrons. So what I'm going to do is make 1 double bond. Now, does it matter which oxygen I create the double bond with? Not at all, okay? These are all equivalent oxygens. So I'm going to pick this one, because why not? And that has a double bond. So it is possible to have a structure like this where there's only 1 double bond. They're not all exactly identical, okay? And this whole molecule has a -2 charge. All right. So what I want you to do now is pause the video and try to draw the remaining 3 structures. So NH3, ammonia, nitrogen, and sulfur dioxide, and then we'll take a look at those. So press play when you're ready to see the answers. All right, so here are the remaining Lewis dot structures, and again, in each case, it's really important to make sure you count the electrons. If you didn't count the electrons for sulfur dioxide, you might have drawn the structure like CO2. But if you did count them, you'd realize that sulfur dioxide has 2 additional electrons, so it only needs 1 double bond rather than 2. All right, so how are we going to use this? So we're going to use these Lewis structures to determine the shapes of molecules. So we're going to use something called Vsepr, or Vsepr theory, and this basically it's an acronym that stands for valence shell electron pair repulsion. So this means that all the electron domains in an atom are going to arrange themselves so they're as far apart from each other as possible. So electrons are going to repel each other and force the molecule to assume certain shapes. Now, the number of electron domains around a central atom will determine the shape of that atom and the angles between the bonds. The actual shape of the molecule is known as its molecular geometry. And just a note, any molecule that only has two atoms is linear, because if I have 2 points, the only shape I can have possibly is a line. All right, so first let's talk about two electron domains around a central atom. So a good example of that is carbon dioxide. So I'm going to use the same simulation we use in class to show you what that looks like. So carbon dioxide has two double bonds, and we can also select this box that says molecule geometry, and it'll tell us that it's linear, but that's a pretty good description, right? Because it's a straight line. Now the reason is we have two electron domains, one in this double bond and one in this double bond. So those two domains, the farthest apart they can possibly be from each other is 180 degrees. Now, if I have three domains, my shape will be trigonal planar, and the bond angles will be 120 degrees. So let's take a look at that. Now, I'm going to remove all these. So BH3, remember that boron is satisfied with 6 electrons. So when I have 3 bonded atoms and no lone pairs, this is trigonal planar. And you can see that the angles are 120 degrees. Now, we call it trigonal planar. Tri is a prefix meaning 3, so there's 3 atoms around a central atom, and planar because, as you can see, it's flat. Now, if one of those bonds was a lone pair instead, there are 3 electron domains still. However, now one of those domains is just a lone pair, so the molecular geometry is bent because we're really only looking at those 3 atoms, but it still has 3 domains. So let's sort of compare those. So if there's one lone pair, we call the structure bent, and the bond angles, you'll notice, are close to 120, but they're just a little bit smaller. And that's because lone pairs are just slightly more repulsive than bonded pairs. So when I replace one of the electron domains that's a bond with a lone pair, it just slightly decreases the bond angles by about 2 every time. Now, if I have 4 electron domains, I actually have 3 options. So let's take a look at those. So, if I have 4 bonded atoms, you might expect that they'd be 90 degrees, but it actually forms a 3-dimensional shape called a tetrahedral, and this allows it to have larger bond angles than 90 degrees. These bond angles are actually 109.5. So an example of this would be methane, CH4. Now, if I replace one of those bonded groups with a lone pair, it still has a similar sort of a shape to a tetrahedral, but since I'm only seeing the bottom 3 bonds, we call this a trigonal pyramid. Trigonal because there's 3 atoms, and pyramid because, kind of looks like a pyramid. Now, as you might expect, the bond angles, again, have decreased a little bit because I've replaced one of the bonded groups with a lone pair. Now, if I have 4 domains but 2 lone pairs, you might have guessed, and you'd be correct, that the bond angles get even a little bit smaller. So there's still 4 domains here, but now there's 2 lone pairs. We also call this shape bent, but the bond angles are based on the fact that it has 4 domains. So here the bond angles are 104.5. Now, if you said 105.5 because you're thinking they go down by 2 every time, that's actually acceptable. That's within the range that IB accepts, and so that would also be within the range that I would accept. All right, so what I want you to do is to pause and try to draw these 3 structures and identify their shapes, and press play whenever you're ready to go over them. All right, so here are the 3 structures. Now, when we're talking about their shapes, for nitrate, it has 3 bonded atoms and no lone pairs. So that means it has 3 electron domains, and so this would be trigonal planar, and the bond angles would be 120 degrees. For CH4, methane, it has 4 bonded atoms, so that would be a tetrahedral. HCN has 2 bonded atoms and no lone pairs in the central atom, so that would be linear with 180 degree bond angles. This is one of those topics that you really do have to practice quite a lot, but practice really does make perfect here. So keep trying, do the practice on Schoology, do the practices in class, and you will get it for sure.